Good afternoon, everyone, and welcome to this invited talk by Professor Max Tegmark from MIT. My name is Fredrik Heinz. I'm from Linköping University, and I have the great pleasure of being the chair today. So Max is born in Sweden and got a bachelor's degree from KTH, but then he basically left Sweden and got his PhD from Berkeley in California, and has spent most of his research time in the US. And he's received numerous awards, including the 2003 Science Magazine's Breakthrough of the Year for his work on the Slow and Digital Sky Survey. His research is mostly known for his work in cosmology, but he has also published work in AI, including a paper together with Jan LeCun, one of our previous invited speakers at this conference. Max is also the president of the Future of Life Institute and has written 2 popular science books, and the latest one of those is Life 3.0, which has raised a lot of attention internationally. And today his talk is going to be called Intelligible Intelligence and Beneficial Intelligence. Please welcome Max Tegmark.
Tackar, tackar. Det är jättetrevligt att vara här. Hela mitt föredrag kommer att bli på svenska. Det var det som var planen, eller hur? Just scaring the rest of you. It's a pleasure to be here and tell you about intelligible intelligence and beneficial intelligence. With technology, what could possibly go wrong? So let me, to illustrate that, change my system preferences. All right. So although most of my research at MIT these days is on artificial intelligence, I've spent my first 25 years of research doing physics. So let's start with a physics example, just to remind ourselves of the big picture. So as an example, the Apollo 11 moon mission was both successful and inspiring, reminding us that when we humans use technology wisely, we can accomplish things that our ancestors could only dream of. But there's an even more inspiring journey that's propelled by technology more powerful than rocket engines, where the passengers aren't just 3 astronauts, but all of humanity. So let's talk about our collective journey into the future with artificial intelligence. My friend Jan Tallinn likes to point out that just as with rocketry, it's not enough to make our technology powerful. We also have to figure out how to steer it and where we want to go with it. So let's talk about all 3 for artificial intelligence: the power, the steering, and the destination, starting with the power. I define intelligence very inclusively, simply as the ability to accomplish complex goals. Because I want to include both biological and artificial intelligence, and I want to avoid this silly carbon chauvinism idea that you can only be smart if you're made of meat. It's really amazing to see here at IJCAI how the power of AI has grown recently. Think about it. Not long ago, robots couldn't walk. Now they can do backflips. Not long ago, we didn't have self-driving cars. Now we have self-flying rockets. Not long ago, AI couldn't do face recognition. Now AI can even generate fake faces or simulate your face, saying stuff you never said. Not long ago, AI could not beat us at the board game of Go. Then Google DeepMind's AlphaZero AI took thousands of years of human Go games and Go wisdoms, put it all in the trash, and became the world's best Go player simply by playing against itself. And the most impressive feat here was not that it crushed human game players, but that it crushed us, human AI researchers who collectively have spent decades handcrafting algorithms for playing games. And of course, AlphaZero didn't crush us humans, human AI researchers, only at Go, but also at chess, which we'd collectively been working on since 1950. So all this recent progress, which is so evident here at this conference really begs the question, how far will it go? I like to think about this question in terms of this abstract landscape of tasks, where the elevation represents how hard it is for AI to do each task at human level, and the sea level represents what AI can do today. The water is obviously rising as AI improves, so there's a kind of global warming going on in this abstract task landscape. And I can say that because I'm in Sweden, not in the US. And the obvious takeaway is to avoid careers at the waterfront, of course, which will soon be disrupted by automation. But there's a much bigger question here, too. How high will the water end up rising? Will it eventually submerge all land, matching human intelligence at all tasks? This is a definition of AGI, Artificial General Intelligence, which has been the holy grail of AI research ever since its inception, even though that's not primarily, of course, what we talk about at conferences such as this one. By this definition of AGI, people who say, nah, there'll always be jobs that humans can do better than machines, are simply saying that they think there will never be AGI. Sure, even if we do get AGI, we could still choose to have human jobs or to give humans income and purpose without jobs, but AGI would still transform life as we know it, with humans no longer being the smartest on the planet. Now, if the water level does reach AGI, well, then further AI development will be driven primarily not by human researchers, but by AI. So this would mean that additional AI improvement could be way faster than the typical human research and development timescale of years, raising the controversial possibility of recursively self-improving AI, rapidly leaving human intelligence far behind and creating an intelligence explosion, and ultimately leading to what's known as superintelligence. All right, reality check. Are we going to get AGI anytime soon? Are we going to get superintelligence anytime soon? This is, of course, a wonderfully fun controversy. Some people get quite worked up about it and say that, only philosophers and others who are not actually active AI researchers take seriously the possibility of superintelligence. But that's obviously an exaggerated claim. Look at this picture, for example. This is from a conference in California last year that I co-organized. You'll recognize on this stage a bunch of colleagues of yours who, some of whom might even be here, who are definitely card-carrying AI researchers. Let's hear what they have to say about superintelligence. So before I asked if superintelligence is possible at all, according to the laws of physics, now I'm asking, will it actually happen? Yes, no, or it's complicated?
A little bit complicated, but yes.
Yes, and if it doesn't, something terrible has happened to prevent it.
That's what I meant.
Yeah.
Yes. Yeah, probably.
Yes. Yes.
Yes.
Yes.
No.
So just because top AI researchers think it's going to happen does, of course, not mean it's going to happen. It just means that this is a fun and legitimate science controversy that doesn't have to be relegated to bars, but it's perfectly appropriate to talk about at science conferences. And controversial it is, of course. Even the question of whether we'll simply get to AGI anytime soon, let alone superintelligence. Some people, like Rodney Brooks, say, nah, it won't happen for centuries. And then there are others, like DeepMind founder Demis Hassabis, who are really more optimistic and are working hard to try to make it happen much sooner. Recent surveys have shown that most AI researchers guess that we will get AGI within decades. Which really begs the question, and then what? What do we want the role of humans to be if machines can do everything better and cheaper than we can? The way I see it, we face a choice. One option is to be complacent We can say, let's just build machines that can do everything faster and better than we can and not worry about the consequences. Come on, if we build technology that makes all humans obsolete, what could possibly go wrong? But I think that would be embarrassingly lame. Let's be more ambitious. Let's envision a truly inspiring high-tech future and figure out how to steer towards it. Which brings us to the next part of my talk, the steering. We're making AI more powerful, but how do we steer towards a future where AI helps humanity flourish rather than flounder? To help with this, I co-founded the Future of Life Institute, as you heard of, a nonprofit organization promoting beneficial technology use. And our goal is simply for the future of life to exist and to be as inspiring as possible. I love technology. Technology is why today is better than the Stone Age. And I'm optimistic that we can create an inspiring high-tech future if we win the wisdom race. The race between the growing power of the technology and the wisdom with which we manage it. But this is going to require a change of strategy. Our old strategy for winning the wisdom race used to be learning from mistakes. We invented fire, screwed up a bunch of times, invented the fire extinguisher. We invented the car, screwed up a bunch of times, invented the airbag, the seatbelt, the traffic light, auto braking, self-driving cars. But with more powerful technology like nuclear weapons and AGI, learning from mistakes is a lousy strategy. Wouldn't you agree? It's much better to be proactive rather than reactive, plan ahead, and get things right the first time, because that might be the only time we have. But it is funny, because sometimes people say, "Shh, Max, don't talk like that. That's Luddite scaremongering." But it's not scaremongering. It's what we at MIT call safety engineering. Think about it. Before NASA launched the Apollo moon mission, they systematically thought through everything that could go wrong when you put a bunch of people on top of explosive fuel tanks and launched them to somewhere where no one could help them. Was that scaremongering? No, that was precisely the safety engineering that ensured the success of the mission. And that's precisely the approach I think we should take with AGI. Think through everything that could go wrong to make sure it can go right. So in this optimistic, proactive spirit, we've organized conferences, bringing together AI leaders and other thinkers to discuss how to develop this wisdom needed to keep AI beneficial. Our last conference, held in Asilomar, California last year, produced this list of 23 principles that have been signed now by over 1,000 AI researchers, including key industry leaders and including a bunch of you here in this room. And I want to tell you about 3 of these principles. Raise your hand if your computer has ever crashed. Ooh, that's a lot of hands. Well, then you'll probably be sympathetic towards this principle, which is that we should invest in AI safety research. As we put AI in charge of ever more decisions and infrastructure, we need to transform today's buggy and hackable computers into robust AI systems that we can really trust, right? Because otherwise, all our awesome new technology can malfunction and harm us or get hacked and be turned against us. And this AI safety work has to also include research on AI value alignment. Because the real threat from AGI isn't malice, like in silly Hollywood movies, but competence. That AGI accomplishes goals that aren't aligned with ours. For example, when we humans drove the West African black rhino extinct, it wasn't because we were a bunch of evil rhinoceros haters, was it? But simply because we were smarter and had goals that were not aligned with theirs. AGI is by definition smarter than us, so to make sure we don't put ourselves in the position of those rhinos, if we create AGI, we have to figure out how to make AI understand our goals, adopt our goals, and retain our goals. So to help kickstart this sort of AI safety research, we went out and managed to do some fundraising. And thanks to the generosity of Elon Musk the Open Philanthropy Project in Jan Tallinn, we were able to do the first ever global AI safety research grants competition for $7 million. It was very stiff competition. 300 teams asked for $100 million, but in the end, these 37 teams came out ahead and have been doing really wonderful stuff ever since. And I'm actually really excited to see a number of these winners here in the audience and who have produced so much awesome research. And this is the vast majority of this research, of these publications, is exactly this sort of wonderful, nerdy, techie research that can be presented at IJCAI. This is just the first 2 years of research that came out of these grants. Since then, there's too much to put on my slides, but Victoria Krakovna has organized a really nice, very up-to-date list of AI safety research papers. So if you're interested in learning more about this technical field or get your feet wet and maybe consider expanding into it, just point your phone at this QR code and you'll see. Another really nice thing that I'm very happy about is that hopefully partly as a result of this research, AI safety is now viewed as quite mainstream, and it happens. There were very few workshops that started happening in 2015, more in 2016, and 2017 and 2018. There's so many that I couldn't fit them on my slide. There was one, of course, very AI safety related, even right here last weekend, and I'm very, very happy that the AI community is now simply owning this issue and driving it and leading it, because nobody knows the issues better than the AI community, and nobody is a better place to solve the challenges. There's also been a bunch of non-profit organizations that have cropped up like mushrooms, helping with this kind of research, and I'm very excited that the industry partnership on AI was formed around the time of the Silvermore conference and is now quite big. So basically, the AI community is being heard. Politicians are listening to the AI community. All these reports are coming out. All sorts of cool stuff. To further help with this, I'm happy to announce that we've managed to raise some more money from Elon Musk to give out more grants. Since there's so much more activity in the space now, we decided to, rather than be a little drop in a big bucket, to focus it specifically on AGI safety rather than just AI safety, because that's perhaps ultimately the most impactful, and that's definitely the least funded. So I'm happy to be able to announce today, for the first time ever, that who actually won this. If any one of you is in the audience, if you can stand up so we can give you a round of applause. So here are the 10 teams from around the world that are going to get to share these $10 million. You can see they're from all over the world. And I don't have time to go into detail about all of these projects, but just to give you a little bit of a flavor. For some stuff, you see there's one project on loss functions or utility functions. There's stuff on value alignment here. Even in the very short term, here's a fun example from OpenAI of where you have an intelligent agent, this boat which is supposed to learn to go around this racetrack. But the goal it's been given is just to get as many points as possible. And of course, it discovers this little bug in how the game was coded and comes up with this totally perverse way of just getting an arbitrarily huge amount of points. This is the sort of stuff it's really good to study and solve in simulation before discovering these sort of things happening in real-world systems, especially powerful ones. If any one of you here is on the job market and interested in these sort of questions, I would encourage you to send an email to me, because I'm recruiting more grad students and postdocs to my AI research group at MIT. The students I have written names for here are the ones whose research I'm going to give a shout out to in a little bit, but they're all friendly and nice, so as you can see. So our group focuses on what I like to call intelligible intelligence. AI that doesn't just work, but that can be trusted, because we understand at least some aspects of it. And frankly, the only way I'm ever going to trust AI that's way smarter than all of us is if I can understand it at some level. I think trust really rests on understanding. And the only way I'm going to trust that an AGI is not going to do something I don't want it to do is if it violates the laws of physics or if I can prove it. Because no matter how smart you are, you can't do the impossible, right? Now, most of my AI colleagues are fairly pessimistic about this. If you think about how able we are going to be to build really advanced AI that we can understand at a meaningful level depends greatly on how we get to the finish line, how we get to AGI. First out in the race was, of course, good old-fashioned AI, GoFi, which we could understand quite well because we generally wrote the algorithms ourselves. But the progress was slow enough that it got overtaken in most subfields by machine learning, of course. And when I talk to the minority of my colleagues who are actually working on AGI, colleagues at DeepMind and OpenAI, for example, most of them are guessing that the ML car is just going to win. It's just going to get all the way, probably with a few more tricks here and there, combined with much better hardware. But that's it, and they've basically given up on the idea that we're ever going to really have a deep understanding or be able to prove a lot of meaningful bounds and theorems. I'm somewhat more optimistic. I'm not optimistic that GoFi is going to come back from behind and overtake ML. That's not going to happen, I don't think. But I do think there's actually a third car in this race, which we haven't paid that much attention to because it hasn't even really gotten off the ground yet and is moving very slowly, which is sort of a hybrid combining the best of GoFi and ML. Those of you who work on automatic theorem proving are well aware that it's much, much harder to discover a proof than to verify the proof, right? Because in the former case, it's NP-hard, you have this exponentially large search space, but for the verification, it's very easy polynomial time algorithms. And in very much the same spirit, you can think of the quest of program induction or creating algorithms in general that do what we want, or very broadly, the quest for intelligence as equal to search. Right? You have some thing you're trying to accomplish, you're trying to find the best one, maybe a nice and simple one, but the search space is, of course, exponentially large, so it seems really hard. But if we can use all the progress in ML to help guide us to finding algorithms, first that work, and then transforming them into simpler ones for which maybe some bounds and things can be proven, then that more intelligible vehicle can be moving much faster than this is moving. This is going so slowly because the algorithms are still created by us, right? But it doesn't have to be this way. If the AI itself is also helping develop the algorithms and verify them, I think there's a real possibility that this could ultimately overtake both of those cars and get there first. And if that happens, I think we'll all be better off for it. There's a greater chance then, I think, that we're going to have some guarantees that the AGI we build will really do what we want it to do. Since my background has been mainly in physics, most of the AI research we do is either using AI to do better physics, stuff like this, or using ideas from physics to improve machine learning in various ways. For example, the paper that just got a shout out here with Jan LeCun and others, and also this paper we did with Joshua Benjo and collaborators, take this idea inspired by physics that the recurrent neural networks should learn best when they're on the verge of chaos, which in physics jargon we describe as having the Lyapunov exponents near zero, which that in ML language translates into the weight matrix for the update being unitary. And we showed that this and various variations of it actually helps on improved state-of-the-art benchmarks. But for the intelligible intelligence stuff, I'm most excited of all about things where we can actually prove stuff or get a deepened understanding of things rather than just make them work. So let me take a little bit of time to give you a little bit more of a flavor for that. So for example, in a couple of papers with Henry Lin and David Rolnick, we talked about links between AI and physics and how we could prove certain things, which was triggered this ridiculously and totally inappropriate, over-the-top kind of media coverage. But what we actually did was we looked at how, basically, there's a dictionary where we can translate all sorts of AI terms into physics terms and back, and thereby port techniques between the two fields. We were able to prove, for example, this theorem that helps understand why deep learning is so useful. We have a situation, we were able to prove, for example, that if you just want to do something as simple as multiply n numbers together, you can do it, of course, with a deep network with only 4n neurons, but you need 2 to the power n neurons if you want to do it with a single hidden layer. So it, of course, has been known since Hornick and others in the 80s that you can do anything like this with a single hidden layer with any nonlinear activation function pretty much. But those bounds didn't say anything about how big the thing was, and 2 to the n rapidly gets bigger than the age of our universe. Whereas as soon as you go a little bit deep, the scaling gets much better. We also were able to generalize this to arbitrary sparse polynomials and to show that, moreover, if you have k layers, instead of this horrible 2 to the n, you get to take the kth root of the n. So what that basically means is that if you don't want to have more than, say, 1,000 neurons per layer, then the number of layers you need only grows as roughly as log 10 of n. So 6 layers or something like that is usually quite good enough for a lot of tasks. We also showed that even though it's well known from the no free lunch theorem that neural networks can only accomplish a set of more or less measure zero of all tasks, it turns out that infinitesimally tiny set of all problems is basically the same set as a almost measure zero set of all problems that we actually care about in this physical universe. So this is a nice way of understanding why our brains develop this particular architecture, because it really ties in very nicely with the sort of things we care about. In terms of intelligibility, something we've been having a lot of fun with also is taking systems like this one, which you've undoubtedly mostly seen, where you have some reinforcement learning deep agent that just gets good at some sort of task, and then does it in a way that's successful but not intelligible at all. When we just reproduce this in our lab, if you ask me how to explain how it does it, here is the answer: just big tables of weight matrices. And then we developed tools to transform this using, again, automated techniques into much more sparse and intelligible algorithms. So then you start getting things like functions like this. R stands for ReLU here. But when you look at this as a human, like if your grad student came up with this, you would be kind of annoyed with them for not thinking, because it's so obvious that this number here is obviously trying to be 1. And all these parameters are trying to be all equal. So you can clearly simplify this greatly. So I'll tell you a bit more about how we do that. But in the end, you can distill this down and you can get you can have an agent which just incorporates these simple equations and plays the game of breakout just as well as that complicated black box code does. Basically what this is doing is, in the end, it's just computing the x and y coordinates of the ball by just computing the second moments of what's in this rectangle here, and then applying this formula, which is just fitting a straight line from a couple of ball positions at different times to see where it's going to put the paddle. So this is an approach that complements, of course, work on all the work you've been talking about at the conference on automatic program learning, like neural program synthesis, neural program induction, rule-based program synthesis, and so on. But this was a very easy problem because the ball just moved in a straight line with no acceleration. So let's look at a harder problem. This is from a paper that we're hoping to post on the archive this week. This is work done with my grad student Kai-Lin Wu at MIT. And take a look at this and marvel at how good your own neural networks are at making sense of this. Your task is to predict where the ball is going to be next. And as a bonus, try to explain to yourself just what's going on here. I'll give you 10 seconds. So, your brains are incredibly good at this, not just at predicting, but also at abstracting out the apparent laws of physics happening here. You very quickly notice that on parts of the screen, the ball seems to just move in a straight line with constant speed, kind of like in Breakout, but there's also another part of the screen, seemingly down here somewhere, where the ball moves in a more weird way that you need to come back and look at more carefully. There also seems to be bounces. There seems to be some kind of boundaries that it can do elastic bounces against, and so on. So, what we do in this paper is we investigate how one can train networks not just to solve this, but actually distill out the laws of physics. It's basically built seeing to what extent you can build a little AI physicist. So we make a bunch of increasingly complicated worlds with magnetic fields, electric fields, springs, nonlinear bounce boundaries. Typically, we'll divide the plane into a large number of different regions, each of which has different physics laws. Now, of course, the easy way to do this is just take some kind of trajectory, and just try to predict the next point from the past n points, the past 3 or past 2 or whatever, by just minimizing some loss function, mean squared error, for example, over some parameter vector that characterizes the neural network that does the prediction here. And that, of course, works. Okay, but accuracy is not particularly great, and the accuracy degrades over time when you want to predict farther into the future, which is very different from what you did in your heads, because you actually extracted out what the laws of physics were and can predict with perfect accuracy for arbitrary times. The result that you get from that simple ML approach also is not intelligible, because here is the explanation of what's happening, which is completely useless to me. And finally, we would also like to see if by distilling it into a simple model, one can actually learn with much less data. So can you do better? Yes, absolutely you can. There are, as you all know, beautiful but NP-hard methods for finding the simplest explanations for things. Solomonoff induction, this whole minimum description length formalism by Rissanen and elaborated by Grunwald, IJCAI-ECAI formalism by Marcus Hutter and his group. And what we basically do is we start with the MDL formalism, and then we use machine learning and various physics-inspired techniques to find approximate solutions, which are not guaranteed to give optimal solutions, but they typically do give the exact optimal solution for our examples, and they do it very fast. One key ingredient is since we're doing minimum description length, it's the loss function we want to use is not the usual mean squared error. So for example, if you were doing something as simple as just trying to fit the green curve to the blue points, and you have some nonlinear parameterized model with 2 parameters, say, that parameterize the green curve, you would find normally the minimum of something that looks like this, or at least in Taylor expansion, it would look like that, around the true minimum. But for the minimum description length thing, what you're trying to instead do is minimize the amount of data, the number of bits it takes to store your errors. So you're going to pay much more attention to every time you cut the error bar on one point in half, you win 1 bit. So the method is much more interested, because of this funny shape here, in further cutting the errors on the points that are already fitting well, than in just doing some half-assed job on the outlier here, whereas the mean squared error thing will sort of do some sort of compromise. And here, so this approach will tend to latch on the exact correct thing, better even in the presence of noise. Another key ingredient of the minimum description length thing is you try to minimize the total description, including both the description of the errors that your model prediction makes and the description of the model itself. Right? So if you have a bunch of numbers in your model that you approximate as rational numbers, this is how many bits you need to store each rational number. You know, simple ones like the integers or 3 halves don't need a lot of bits. More ones with huge numerators and denominators need lots. And then if it turns out that the minimum loss, the minimum description length for the data is at some particular point here, what you do is you add this curve from the last slide to those dots, and then it's going to distort the point cloud. And now the one that's lowest, which is the one you want, is not going to be 0 or 1 or 2. It's going to be, in this case, 3 halves. This is, again, this raw approach would, again, take a ridiculous amount of time because you would have to enumerate all these rational numbers. It takes forever. So what we do instead is we do after we've done just the standard gradient descent search, we do a continued fraction expansion of each of the parameters that we find. And we look at all possible truncations and to see which one minimizes the total description length. So if you have a number in there that is not easily approximated by a rational number like √2 or something, you see it's kind of the total number of bits cannot really be reduced. It's incompressible. Whereas if there's a parameter that's trying to be something simple, this gets discovered very fast. You can ask me for the paper afterwards if you want to see details. Short answer is we're quite happy with how it works. This is just a tiny baby step towards more intelligible intelligence. But I'm excited more broadly about the whole field of trying to combine all the tools for machine learning to make more intelligible GoFi stuff work better. All right, in my final few minutes, let me tell you about the other two Asilomar principles I want to give a shout out to. So first of all, I said, okay, we should invest in AI safety research. And I tried to convey why I think it's important and fun. Second, there was very broad agreement that we should mitigate AI-driven income inequality. I think that if we can figure out how to grow the economic pie dramatically with AI, and we still can't figure out how to share this pie so that everyone gets better off, then shame on us. And for people who, since I live in the US now, when people tell me that it's impossible, I just wish they would do what you did and come visit Sweden. Finally, another Asilomar principle is that we should mitigate AI, that we should try to avoid an arms race in lethal autonomous weapons. And the idea here is that science can always be used for new ways of helping people or new ways of harming people. For example, biology and chemistry are more likely to be used for new cures or new materials than for new ways of killing people, right? Because biologists and chemists successfully pushed for banning biological and chemical weapons. And in the same way, most AI researchers want to stigmatize and ban offensive, lethal autonomous weapons. Surveys on this and a lot of open letters and such. And it's important. There's a lot of confusion about this, though. So when you think lethal autonomous weapons, don't think about some silly Hollywood flick with bipedal robots or something. Think about something cheap that you could just launch from the back of a van, which is lightweight, it just has navigation, basic face recognition, or whatever. Now, this is if you think to yourself, yeah, I don't know about this. I'm against the ban on lethal autonomous weapons. Chances are that there's very interesting arguments that you have in mind. So let me just quickly run through some of those. For example, you might say to yourself, well, I'm not a pacifist. I'm not a pacifist either, truth be told. But opposing biological weapons does not make you a pacifist. And analogously, this is not against weapons in general or helping the military or anything. It's merely about an extremely controversial subclass of weapons. If you support today's drone warfare or you support autonomous missile defense systems, neither of those count as lethal autonomous weapon systems. Drones don't because they have a human in the loop who makes the kill decision, and these autonomous missile defense systems don't count because the word lethal in lethal autonomous weapons means that this is a weapon that targets humans, not missiles. Another really interesting critique is the one that, surely lethal autonomous weapons are good because we'll save lives by just having robots die instead of soldiers in future wars. But this assumes that after we get lethal autonomous weapons, the specific battles, the numbers, times, locations, places, circumstances, will be exactly the same as before, which is about as silly an assumption as assuming that after we got cruise missiles would be used in exactly the same context that we previously used spears, right? And so obviously autonomous weapons would be used in new contexts. That we could get a new arms race flooding the black market with low-cost anti-personnel weapons that could be used by terrorists and despots and criminals. And also, the threshold for starting wars will be lowered if there's literally no skin in the game. There are a lot of other objections I won't have time to get into here, but I'm happy to chat with you over coffee about. I'll just mention one more, which is, won't lethal autonomous weapons be more ethical ultimately than human soldiers? Perhaps not now, but maybe in 10 years, since after all they aren't afraid of dying and don't get stressed out. Well, even if technology were one day to reach this point, which it hasn't yet, I would say, then how would it be easier to enforce? How would it be easier to enforce that enemy autonomous weapons are 100% ethical than to enforce that they aren't produced in the first place? Also, one cannot just consistently claim that well-trained soldiers of civilized nations are just so bad at following the rules of war that robots can do better, while at the same time claiming that rogue nations, dictators, terrorist groups are so good at following the rules of war that they'll never choose to deploy these weapons in ways that violate the rules. So, in short, I think the case is actually quite good for why we should follow the biologists and chemists and try to also safeguard our field as a predominantly civilian field, to not have it get hijacked entirely by military destabilizing things for lethal autonomous weapons. And I'm happy to report that one more little news item here. We're also releasing today this pledge. So rather than to sit around and wait for politicians to discuss this endlessly and not do anything, we have here 160 tech companies, including Google, DeepMind, and also a whole bunch of universities here on the left side. Even I'm very happy that both the European Association for AI and the Swedish AI Society are helping organize this meeting, have signed on to this, are simply saying, okay, we're not going to wait for politicians. We pledge that we are not going to build lethal autonomous weapons. If you feel the same, then you can join this list of individuals pointing your phone at this QR code and also take this pledge yourself. The key sentence is just that you will not yourself participate in or support the development, manufacture, trade, or use of lethal autonomous weapons. And in addition to this, there are a bunch of companies who have said that they are not building lethal autonomous weapons, and there are a bunch of countries. So they're saying that they want a ban, including some quite big ones like China. And I have to say, though, being Swedish, it is embarrassing for me to stand here and notice that Sweden is not on the list. So anyone here involved who has connections in the Swedish government, I would love to talk with you, because I think Sweden has had a fine tradition of not just being high-tech, pushing high-tech, but also being out there advocating for its good uses. It was kind of energizing that while I was putting the final touches on this morning, these news articles started popping up about this announcement that I was about to make here. So there's some sort of closed time-like loop going on here. And so with that, let me just wrap up by saying that I think it's a very good idea in the very short term to ban lethal autonomous weapons and think how we can how we can share the great wealth that's going to come out of AI, and in the longer term also do enough AI safety research, not just on short-term stuff like cybersecurity, but also to make sure that we can get it right even if we get to AGI. And I think if we do those things, I'm really optimistic that AI can become the best thing ever to happen to humanity, that we can end up building not AI that overpowers us, but AI that empowers us. Thank you.
Thank you very much. Unfortunately, in sake of time to keep the timetable, we don't really have time for questions, and actually Max has to run off to the next item, but you will be around for the rest of the day, and will you be here tomorrow maybe?
I think yes to both questions, and so please do corner me in a coffee break or whatnot, and if you don't corner me here, just email me, and I'd love to continue this conversation. Thank you.
Thank you.